To our series on alkyne reactions. In the previous video, we explored the hydroboration of alkynes, which yields aldehydes or ketones. In this video, we shift our focus to reduction reactions. Our goal is to increase the hydrogen content of the molecule. Because alkynes can undergo two sequential reductions, we have three possible outcomes, depending on the reagents we choose. Complete reduction to an alkane, partial reduction to a cis-alkene, partial reduction to a trans-alkene. We will learn how to control these outcomes and, in particular, examine the mechanism responsible for forming the trans-alkene. Part 1. Catalytic hydrogenation. Case 1. Complete reduction to an alkane. Treatment of an alkyne with hydrogen and a metal catalyst such as palladium, platinum, or nickel leads to rapid hydrogenation. The first equivalent of hydrogen forms an alkene, but the alkene is still highly reactive toward hydrogenation under these conditions. So the reaction proceeds immediately to the second addition. The final product is a fully saturated alkane. Case 2. Partial reduction to a cis-alkene. To stop the process at the alkene stage, we use a poison catalyst. The most common example is Lindlar's catalyst, a palladium catalyst deactivated with lead acetate and quinoline. Because hydrogenation on a metal surface proceeds through syn addition, internal alkynes are reduced exclusively to cis-alkenes. Note: we will only cover the key outcomes of Case 1 and Case 2 here. If you are interested in the detailed catalytic mechanism, please refer to the video Alkyne Catalytic Hydrogenation. Part 2. Dissolving metal reduction. Partial reduction to a trans-alkene. To obtain the trans-alkene, catalytic hydrogenation is not suitable because the metal surface enforces syn addition. Instead, we use a different reduction method known as dissolving metal reduction, employing sodium or lithium metal, dissolved in liquid ammonia at low temperatures. Unlike the concerted syn addition of catalytic hydrogenation, this transformation proceeds through a stepwise radical mechanism that naturally leads to the more stable transgeometry. The overall sequence is an electron, then a proton, followed by another electron and another proton. Presenting it this way makes the sequence easier to remember. Step 1. Electron transfer. Formation of a radical anion. A sodium atom donates one electron to the alkyne, partially reducing one of the pi bonds and generating a radical anion. This intermediate contains one carbon bearing most of the negative charge, the other carbon carrying an unpaired electron. To minimize electron-electron and electron-radical repulsion, the substituents adopt a geometry that reduces repulsion, leading toward the trans-arrangement. Step 2. Proton transfer. The radical anion is strongly basic and immediately deprotonates a molecule of NH₃, the solvent, forming a CH bond and producing a vinylic radical. Step 3. Second electron transfer. A second electron from sodium reduces the vinylic radical to a vinylic anion. The anion maintains the established trans-like geometry to minimize electron repulsion. Step 4. Second proton transfer. The vinylic anion abstracts another proton from NH₃. This final protonation completes the anti-addition of hydrogen, producing the thermodynamically favored trans-alkene. Let's summarize the three distinct reductions for alkynes. Alkynes are fully reduced to alkanes when H2 is added in the presence of a metal catalyst. Alkynes are partially reduced to cis-alkenes when Lindlar's catalyst is used. Alkynes are partially reduced to transalkenes when sodium, or lithium, is used in liquid ammonia. To wrap up, those who wish to deepen their understanding of alkyne reduction are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.